Okay, in this lecture, we're actually going to do some example problems of both passive and active filters. I'm going to do these together so that we can kind of compare and contrast. And these are coming from your homework assignment that was posted online. It's a recommended homework assignment. And these are the last 3 to 4 problems on the assignment. They pretty much cover everything with what we've done so far. So we're going to start with problem 1, which says design first a passive and then an active low-pass filter. With a cutoff frequency of 10 kilohertz using a 1 microfarad capacitor. So the first thing that we need to do, and then the other thing that you're asked to do is you're asked to use MATLAB, plot the Bode plot for the filter transfer function. We haven't covered Bode plots yet, but we will come back and do that so that you can see that everything is consistent with the suggested homework, and that Bode plots are included on the first exam, so that's going to be important. All right, so first a passive and then an active, and it is a low-pass filter. So the low-pass filter for the passive, and we'll use an RC. It does tell you to use a 1 microfarad capacitor, so that kind of tells us that we're using an RC. Also, notice that actually this frequency is given in terms of hertz. So it's actually F, not omega, and we're going to have to convert to omega before we can do the problem. Okay, so here's our passive RC filter. This is the low pass, taking the output across the capacitor. Okay, and if F is 10 kilohertz, omega is 2 pi F, so it is 6.28 times 10K, or 62.8 kiloradians per second. Okay, or 6.28 times 10 to the 4th radians per second. Okay, so that's our omega C. And the transfer function for this filter is 1 over RC over S plus 1 over RC, where omega cutoff is equal to 1 over RC. And so if C is equal to 1 microfarad, R is what we need to solve for. So we take omega C, which is 6.28 times 10 to the 4th radians per second, and we set that equal to 1 over R, times 1 times 10 to the minus 6. So 1 over R is 6.28 times 10 to the minus 2. So R is 1 over 6.28 times 10 to the minus 2. So let me pull out a calculator. Take me just a minute to open that up here. So 6.28, 1 over x is 0.159 times 10 to the 2. So 1.59 times 10 to the 1, or 15.9. Let me just double check that decimal. 0.00628. 1 over x. Okay, I'm actually getting 159. Let me more time. 0.628. Yeah, 15.9, and that's ohms. So our answer then, our solution is we have 15.9 ohms, 1 microfarad. We have to show the input because the input and the output define the properties of the filter. So there you go. This is your sort of finished design right here. Okay, now equally important is to write the transfer function and fill in R and C. So H of S now, so let's track back and find what omega C was. It was here. So H of C is 6.28 times 10 to the 4th over S plus 6.28 times 10 to the 4th. So just want to re-emphasize that first of all, in a transfer function, H of S or H of J omega, either one, you're always dealing with omega. When you solve for 1 over RC, that's units of omega. And so if you're given hertz and you are going to find a transfer function, you've got to convert first to radians per second. If you want to know a solution in hertz, you're going to get radians per second out of your transfer function, and you've got to then convert to hertz. So just be aware of those units. All right, now let's talk about the active form of this. So the active high-pass filter is an op-amp filter. And I know that you're going to be able to go online and you're going to be able to find alternative forms. But I'm going to tell you that this is the form we're using in class. So this is 1 over SC, this is R, this is R. We'll do this with a gain of 1 because we were not specified a gain. This is our V of S, N, and this is our V out of S. And so just like in the previous problem, H of S is 1 over RC over S plus 1 over RC, where RC is the cutoff, and we want the same cutoff. So obviously we're going to have the same value of R and C. So H of S, the transfer function, will be the same as it was in part 1, which was the passive filter, only now we have an active filter. So if we want to show our final design, R was 15.9 ohms. So we will set the input resistance to 15.9 because we want a gain of 1. We also want the feedback resistor to 15.9. And the capacitor is also, what were we, 1 microfarad? Yes. The capacitor is also 1 microfarad. Here is your Vn. Here is your V out. All right, so there's your op-amp circuit. You don't have to draw this ground connection if you don't want to. It's just, it can be just as long as you show where the output voltage is coming from. I'm just doing that to show you different ways of illustrating this. So that's your low pass filter example, we'll now do, that's pretty much that. And notice the transfer function once again is the same. The cutoff frequency is the same. It's 1 over RC. The only difference is you have this op-amp. All right, now let's look at question 2. Question 2 basically says, it's very similar. It says you want to design first a passive and then an active high pass filter, you need a cutoff, and once again, this is given in hertz, 1 kilohertz. C is 0.5 microfarads. So before we do anything else, we need to calculate omega C. So that's going to be 2 pi times 1 kilohertz. So that's actually going to be 6.28 kilohertz. Okay, so the high pass filter, the circuit is where you take the output for the passive one across the resistor. So this is that circuit in the Laplace domain. We have previously derived that the transfer function is S over S plus 1 over RC, and we previously mentioned in multiple lectures that the way you tell that this is high pass and not low pass from the transfer function only is that it's got an S in the numerator. So I could invert this problem, give you a transfer function S over S plus 10, and ask you to draw me a passive circuit that would achieve that. You would know that that would be the high pass version of that circuit. Okay, so 1 over RC is 2 pi FC, which we've already done, so it's 6.28 times 10 to the third. So R is what we're solving for, so 1 over R, 6.28 times 10 to the third, and our capacitor is 0.5 times 10 to the minus 6. So if we do that, we get 3.14 times 10 to the minus 3. So R is 1 over 3.14 10 to the minus 3. So if I do that real quick on the calculator, 0.00314, 1 over x, I get 318.5 ohms. Okay, so now I want to point out that this circuit that's sketched in the Laplace domain is actually not a circuit. It is a Laplace equivalent of a circuit. So to actually show the circuit, we need to go back to the time domain where we're dealing with actual elements. So here's our capacitor. We've already said it was 0.5 microfarads. Our resistor for this passive circuit, we just calculated to be 318.5 ohms. This is where we take our output. This is where we put our input. And our transfer function, once again, the problem is not complete until you actually show the transfer function with numbers. And we determined that omega cutoff was 6.28 times 10 to the minus third. Okay, so that's your passive high-pass filter design. So now let's look at an active high-pass filter design. So from the previous lecture, the high-pass filter, first order active, looks like this. Once again, because we want to do the same design, we've got a gain of 1. We are going to have the same transfer function. As we had before, because we're basically trying to achieve the same thing. Here's our input. Here's our output. R is the same as it was for the, R is the same as it was for the passive filter. 318.5 ohms, and C was specified in the problem. Okay, so active and passive high pass filter. All right, I'm gonna stop this video so that these videos don't get too lengthy. And what we'll do in the next video is we will do a bandpass filter design.